Okay, this will be the last part of chapter 2, 3, and 4, the grasshoppers case study, some of the key terms that go along with this one. So, it starts off with the 4 properties of water. So, water is unique because I'm going to start with the floating of ice on water. So, we know that oxygen binds to 2 hydrogens here, and there's often a hydrogen bond between 2 of the water molecules. And this causes all sorts of unique properties to form. The first and most important one probably is that ice floats. And without ice floating, we would have lakes that would freeze solid, because the ice would form and it would sink to the bottom of the water. And it would sit there, and then there would be more ice form on the top, and that would sink down. So when ice floats, it creates sort of a barrier between the cold air that's in the wintertime and the water below it. So that prevents all of the water from freezing in a lot of lakes. Shallow lakes, of course, will still freeze solid, but not all lakes do that. So ice floating is really important. When ice goes from a liquid to a solid, which means, in the form of water, to ice, it expands. And when it expands, and you know this from living in Minnesota, like our roads get ice in them. They expand underneath the roads, and then it cracks the pavement that we drive on, or the blacktop or whatever. So ice expands from its water state, and that's really the only material that actually does that. Most all other materials shrink down, and then as a result, as they shrink down, they don't float like ice does. So that's one of the most important properties, one of the most unique, because it's the only material that actually floats when it's a solid. If you think about anything else that is a solid, it will sink in the liquid form of it. So if you had like liquid iron, for example, and you toss a chunk of iron into it, it would sink to the bottom of it. The second one then is pretty easy. This is cohesion of water. So this is where 2 water molecules stick together. So this is that hydrogen bonding that we saw over here. The third one is temperature. So water is really good at absorbing energy. So it takes a lot of energy to heat up water. It takes a lot of energy for water to cool down. So if you converse that with like alcohol, I'm sure you've used rubbing alcohol before. You put it on your skin, and it cools off. It feels like it cools off your skin because it's evaporating so quickly. Water doesn't do that generally, unless you're like in front of a fan or the wind or something like that outside, like coming out of a lake or pool. Alcohol will do that very rapidly. Water takes a lot more energy and a lot more time for that to occur. So when we look at like places like Duluth, or the North Shore of Minnesota, or the coastline in California, and then the East Coast, those places have like moderate temperature changes throughout the year. It takes they're less extreme in those places. So the extreme places, if you think about those, like desert, so these will have really high highs, and then they actually get really cold also during the nighttime. So there's a big extreme change. I always relate it to this too. Like for me personally, I have a friend who lives in California, like in Northern California, and he always talks about how it's like always like 75 degrees and sunny there. So it doesn't matter the time of year or anything, because he's living on that coastal area where the temperatures get moderated to being sort of like that same all the time. And then the last one here is the universal solvent. So water's in almost everything. It's in our bodies. almost everything dissolves in water. We know that things like oil and fatty material do not dissolve, but most everything else does dissolve very well. So water has these sort of 4 key things to it, and that's really helpful for allowing it to life on Earth here for us. I'm going to briefly go into acids and bases here. So the big thing is being able to sort of identify what's an acid, what's a base, and what will it do to us. So acids generally have a hydrogen, and bases generally have an OH group, a hydroxyl group. So an example of this might be sodium hydroxide. That's a pretty strong base. And acids like hydrochloric acid, HCl, hydrogen with a chlorine on it. So what happens when these things interact with water? So if we take HCl and we add water to it, that's going to produce this thing called hydronium ion and chlorine. And so this is the part that is the acid. Sometimes you might see this as just H+, and that's also an indicator for an acid. So anytime we have this group forming, that is a property of an acid. And then a base, like sodium hydroxide, is going to sort of do the opposite here. So the reaction here is a little bit different in that the water actually acts as a solvent here, like we talked about in the previous case. And what this makes then is a sodium ion and an OH ion. And then there's still water around in the environment. And so this part will actually sort of interact with this water molecule, and it'll pull a hydrogen over to it, right, to make water over here, but now we're left with an OH minus group on this side. And so this will kind of bounce back and forth between those two states. The sodium ion, which we will see this, throughout the course, that sodium is important for our maintaining electrolyte levels and balancing water in our cells, out of our cells, and things like that. So bases, generally, the way to identify those is they will produce this OH group. So if we have this, though, we have some things in our bodies called buffers. And so buffers especially oppose, so they're sort of like let me erase that, sorry. They're sort of like the anti-acid in our bodies. We consume a lot of things that are acidic, much more than we consume things that are basic. Basic things are generally bitter tasting, and so we don't eat a lot of them. And bitter foods, bitter things also tend to have a toxic property to them. So it's something that we generally avoid. Whereas acidic things, like an orange, for example, is going to have a lot of acid in it. So our body has to be able to neutralize that acid. So what these buffers do as an anti-acid is they have these free OH groups floating around. So if we were to consume, let's say, this hydrochloric acid over here, in oranges it's actually a little bit different of an acid, but it does the same thing, right? All acids produce this H3O plus group. This OH group is going to be able to react with it very well. I'm going to draw it down here in the bottom in yellow. So if we have that an H3O plus group, and I'm actually going to get rid of the chlorine because that is also an electrolyte that will go and be used, and it'll go through our urine and get excreted out. So that kind of goes away in our body, in our biochemistry. But H3O plus OH minus, this is the buffer. This comes from the acid. When you have an acid and a buffer, and the buffer is actually, hint, a base. So if you remember this from chemistry, these do what's called neutralize each other. And so one of the hydrogen is going to move over here, and we're going to get H2O plus HO H, which is actually H2O. So these balance each other, and we get 2 molecules of water at the end. And so buffers are really good at being antacids, especially with our bloodstream, because we can't have our bloodstream, we can't have our urine, things like that, dropping in their pH values. So remember that pHs that are high are bases, and pHs that are low are acids, and 7 is neutral. So if our bloodstream drops too much, or our other parts of our body get too acidic, then we can have damage being done to them. And so buffers help to take care of that. And buffers are generally antacids because they prevent acids from reacting with our stuff. Because you can eat as many oranges as you want and you're not going to become too acidic. Our buffers in our body are always going to be there to kind of balance that out. So that's the end of chapter 2, 3, and 4 here.